So now that we've talked about a few approaches and have an understanding of how to go about approaching geospatial analysis, in this notebook, we're going to specifically do some exploratory spatial data analysis, and then we're going to use a k-nearest neighbors approach to do some machine learning. The tools that we'll use here that we haven't talked about before are Shapely and GeoPandas. Shapely is necessary anytime you want to work with maps and visualization because Shapely objects are what allow you to create the map in the background and then add data on top of it. GeoPandas is one approach to doing geospatial analysis in Python. We're going to be using this here, but if you have a different approach that you know, you're free to use that for your final projects. The reason we're using GeoPandas here is because it works well with the Pandas data frame that we've been talking about all quarter. And the idea here is if you have a Shapely object and a data frame with data that's geospatial, you can use these together to create a visualization. So we have data that we'll be using here in the notes, and it requires you to download it so that we can use that information. And of course, we have a whole bunch of different tools we're going to use throughout, most of which are going to be familiar. We're going to be doing some plotting. We have Pandas and NumPy, and we also have GeoPandas, which we'll refer to as GPD. We're going to be using Shapely objects and doing a bit of machine learning. And then we have warnings, and we're only going to display a few rows. Okay, so we have our setup ready to go. So let's talk some basics about GeoPandas. There are some files available from GeoPandas directly, so they have a datasets module. We're going to be using the Earth, the low-res version, and then the cities from the Earth, storing these in world and cities. So when we read those in, if we take a look at what those data look like, this is a GeoPandas data frame. So what we have here is information about the continent and the place, information about the population estimate there. And then what's unique about this GeoPandas file is you have the geometry, and this polygon is going to map onto a map that you want to visualize. So this is the shape information that you need to plot geospatial information. When we look at our cities output, forgot to run the cell before. All right, so we have our world data, we have our cities data. What we see in cities is this is information about specific cities, and then you have a point. So rather than a polygon, this is just a single point, a single location on your map, and these points map to the polygons so that you can overall create a map. So if we wanted to plot population estimates, what we can do is create a plot of the world. So there's a plot function that exists for GeoPandas objects. You specify which column it is you want to generate the population estimate for. Here I've just added an axis and then specified that I want the legend to plot. And we very quickly see a few countries that jump out at us as we know that they have the highest population in the world. So you can take these objects very simply and create maps that visualize the information you're interested in. You just have to have it in the GeoPandas format. I'm going to delete that question there. Often I'll ask students how to improve this, and that, we've talked about the fact that lighter colors should be the lower values and darker colors should be the higher. And this one uses diverging colors, yellow and blue. So a light blue to a dark blue or a light green to a dark green would be more appropriate for continuous data. This is another example of how defaults in plotting packages are not always ideal for actually how we interpret information. Okay, beyond that, we could use a different color scale. So here we use a lighter color scale to a darker color scale. And this then shows you and really highlights those with the darker color. So this is the CMAP argument here where we specify we want to use green, blue. Okay, beyond that, you can plot data that allows you to look at, say, different information throughout the world. So if you wanted to look at GDP per capita rather than just population, you could plot those information by just changing a tiny bit of your code. And we can see places where GDP per capita is quite high, and then what the overall patterns look like throughout the world. So this is not meant to B, an analysis here, it's just meant to get you some familiarity with the plot function and using that on a GeoPandas object. Now, you might be then curious of those places in the world that have the highest GDP per capita, and you can operate on this the same way you would a PANDAS data frame, right? We can ask for places where GDP per capita, which we calculated above, taking the GDP and dividing it by the population estimate. And we can then look to see which places in the world have the highest GDP per capita and get information about those. So again, you're creating maps, but the underlying data frame looks very similar to a PANDAS data frame because we're working with GeoPandas. You can also combine maps. So what we're looking at here is the population estimate map we started with, and we're plotting then cities on top of it, right? You can take these points and plot them on top of the shape objects. And here I'm specifying that I want to use points and make them red and make the marker size 5. And we can then plot different points throughout our map. Things that look out in the ocean are on islands. And you can start to combine different pieces of information when plotting in GeoPandas. Okay, so with that whirlwind tour through GeoPandas, let's now use that information to carry out a geospatial analysis. We'll talk about the data we're using here. We'll do an exploratory data analysis, mostly looking at some visualizations, and then we'll jump into analysis. The data we're going to be using are district level data from Berlin. So we will read these data in from a SciPy 2018 geospatial data workshop. If we look at these data, we know that we have 138 observations and 4 columns. If we look at just the first few, what we see is there's information at about what district there is, the district group, the median price, and we're going to be talking about Airbnb prices in that district, and then information about where that district exists on a map. If we want to just get an idea of the distribution of median price within our data set, we can go back to our typical approaches using Seaborn or whatever you like to use to generate visualizations. And we can see across our data set, there's this distribution of median price. We see that there are a few districts that have higher median price relative to everybody else. So this gives us information about the overall distribution, but we don't have information about how the data are spatially related. So to do this, we would need to plot that information, median price for each district, onto a map. And we can do that again, because it's a GeoPandas object, using the plot command function. And here we see a map of Berlin. Each district has a different color on this choropleth map, with the darkest colors having the highest median price. So we see here in the center of Berlin, and then out here towards the southeastern region, have the highest colors. Now, unless you know something about the area of Germany and Berlin, interpreting what's going on is maybe a little tricky, but we can see that there is some variation in median prices across the regions and the districts. Now, we've talked about spatial autocorrelation before. If the prices were distributed randomly, there would be no clustering of similar values. To visualize the existence of global spatial autocorrelation throughout our region, let's take it to the extreme. Let's look at the 68 districts with the highest Airbnb prices and those with the lowest prices. To do this, we're going to do one-hot encoding, or just take information and split it into 2 groups, high and low, with the code here. And what we can do is then take this new column and generate a map. So 0 is going to be the white areas. These are going to be the places with the lowest median prices, and the black are going to be those regions with the highest. So we've just made this binary rather than take the actual median values. And we can see very clearly from this that there's certainly spatial autocorrelation, right? There are regions that have similar median prices and then places with less. Now, it's not just that the eastern part and the western part all have the lowest and highest, but there is spatial relationships between the districts. All right, so we've done some spatial exploration. How can we then go about understanding, if I were a person trying to predict what the price would be within a region, in a district, how would I go about doing that? Now we can use kernel regression, where we're going to borrow strength from nearby observations. We saw that they are related. So how do we go about utilizing that to generate predictions? Now, nearby has two different meanings when we're talking about geospatial data. There are two simultaneous senses of what is near. You can have, for a given Airbnb listing, something that is similar in spatial position, and this would require you to use a spatial kernel regressor, or something that is similar in attribute, right? Something could be similar based on how many bedrooms it has or how many bathrooms it has. So we have similar in attribute and similar spatially, meaning something nearby in physical geospatial space. So the question here is, if you were going to take Airbnb listings and try, given a listing, to predict what price it should have, what features would you consider, including in a model, to predict an Airbnb's nightly price? We have median prices we've been looking at. What if we were to look at specific Airbnb listings? So I usually pose this to the class and we come up with a whole list. So think about it now. What we're going to do here is try to predict the log, and we'll talk about why, of an Airbnb's nightly price based on how many people the Airbnb can accommodate, its review scores rating, its bedrooms, the number of bedrooms it has, the number of bathrooms, and the beds. So these are going to be our attributes we're using. So what we're going to be doing here is using a new data set called listings here. What we're doing is reading in the listings and then looking at what these listings are. What we have when we're talking about the specific listings are a whole bunch, 20,000 different listings, a whole bunch of attributes. If we look at just the first few rows, we see we have a whole bunch of information. When this was scraped, the name of the listing, some summary, this is in German. If you read German, it is certainly more informative to you. But we then get to information about the attribute, about the listing, how many reviews it has, whether or not it's bookable. So we get information about the listing. And our outcome variable is going to be price, right? This is what we are interested in predicting, generating a model that, given information about an Airbnb, what can I say its price should be? This is just a plot of latitude and longitude, and the points are colored by their price. So we have each Airbnb listing, and we can see that there are higher prices toward the middle and lower prices out towards the outside of the Airbnbs in our listings data set. If we just look at a distribution of price, we see that it has this long tail, that the vast majority fall between, about 20 and 80, but there are some that are much more expensive. So when I mentioned we're going to be trying to predict the log price, this is because we are going to do a log transformation of these data to get these on to a normal distribution scale to make predictions a bit easier. So here we see a map of our log prices. Again, if we look at the distribution here, we can see a pretty normal distribution now, and that our predictions are not going to be driven by just those that are much different than the vast majority of the data in our data set. Okay, so now we jump into talking about the models. I mentioned which features I'm including in the model we're going to be working with: accommodates, reviews, bedrooms, bathrooms, beds, and then we'll need information about the price and, of course, where it maps onto our map, our geometry. So these are going to be our model data. These are going to be our attributes. So anytime you see X, this will be predictors, what we're going to be using for our model. And anytime you see Y, that's going to be our outcome. That's going to revolve around price. And it's going to be the log of our price. So we have our predictors, we have our outcome. Now we still need the spatial coordinates for each listing, because we have things that are near in attribute space and things that are near in geospatial relationship. So to do that, we're going to get our coordinates for each listing. And we can then use two different models. We can use from scikit-learn their neighbors regressor. They have one in where you can use the observations around each focal site, k-nearest neighbors or radius neighbors, where it's going to consider all observations within a fixed radius around your site of interest. These methods can also use inverse distance weighting to rank the relative importance of sites around each focal site. so that things that are near are given more weight than things that are far away, even if they're in the space that you're considering. So know that there are k-neighbors approaches, there are radius neighbors approaches, and all of these are available to you for your final project. What we're going to do is then get our training and test data set as we have before. We'll use an 80-20 split. So we're taking our shuffled data, getting our training and test data set here. And we're going to fit 3 models. One that only uses the inverse distance weighting of the nearest 100 neighbors in geographical space. And so that's going to just take information about what's nearby and their prices. Attribute space is going to use inverse distance weighting on the nearest 100 neighbors in attribute space. So those that have the most similar features. And then both. One that uses inverse distance weighting in both the geographical and attribute space. So each time we're going to fit our spatial model using k-nearest neighbors, our attribute model using the attributes, the information about the Airbnbs themselves, not their location, and then one that considers both. So we will have a spatial, an attribute, and a both. To score them, I'm going to look at the scatter plot and the percent of explained variance. So what I'm talking about here is when I train these 3 models and make the predictions from the spatial, the attribute, and the combination, I can then look at the percent variance explained for each model. If I look at the spatial predictive model, it is explaining all of the variance in the data. If I look at the attribute model, it's explaining 47%. And then the both is not doing very well. It is predicting almost none of the variance in the model. So when we look at these predictions, here's what I'm talking about. Here is the both data. So the predictions from the both model, we took spatial and features into consideration. What the actual price was is on the x-axis, and what the prediction was on the y-axis. And you can see that 0% of the variance is explained here. This is not doing a good job predicting what's going on. If I change what's in the code here to attribute, we can see that there is some relationship, right? We start to see that there is a trend between what the true price was and the predicted price in our training data. If I look just at the spatial data, we can see that it totally fits the training data, and that what the true price is exactly what the predicted price was, and that matches up with what we saw when we looked at the variance explained. Now, we don't just care that it works well in the training data. We want to see how it's working in the test data. So we're passing in the test data using the models we created earlier, and then storing these in Y predicted for each of the models. When we look at variance explained here, now we see in that model that had fit 100% of the variance in the training data, it's only explaining 12%, 13% of the variance in the spatial data. Our attribute model is explaining 31-ish% of the variance, and that both models still performing poorly. Same idea here is if we look at the spatial model, we can see there's some relationship between what the true price was and what was predicted in the test data set. We see this improve a little bit in the attribute model, and then the both model, which we know is not performing well, doesn't show any relationship between what the true price was and what was predicted from the model. Now, none of these models is performing particularly well. There are a whole bunch of considerations, and this is often what happens when you're trying to generate a predictive model. You start simple, you include some features, you build a model, and it performs meh. What you have to do is consider whether or not the features you're including in your attribute model are the correct ones. Is there a way to include reviews? Is the text in the reviews? Is there a way to include more information about the Airbnb listing itself? Does the model tuning need changes? I used k-nearest neighbors. Maybe we should be using radius nearest neighbors. Maybe we should be using a different approach other than nearest neighbors. And that has to do with model tuning and model selection. I randomly chose 100 nearest neighbors. Maybe it should be 10. Maybe it should be 200. There are other additional parameters within the model you've chosen. And if that model is not behaving well, you can choose a different model and make sure it's an appropriate model for the task you're trying to complete. Now, One method that can exploit the fact that local data, nearby sites, may be more informative at predicting an outcome at a given site than distant data is geographically weighted regression. So GWR is available for you to use. And if K-nearest neighbors isn't quite cutting it, this is a place that you can turn to optimize the sense of local with regards to your data. So that package exists and you are free to check that out if this is something you're interested in learning more about. All right, with that, I encourage you to look back at places you were confused here, run the data yourself, make sure you understand what's going on so that you have a sense of how to work with geographically and geographic data that are spatially related in Python. Don't forget to take the Canvas quiz.